Hello, welcome to the tutorial session 3 of the online course on pericyclic reactions and organic photochemistry. We are in module number 23 of week 5. In this particular module, we will consider several problems involving sigmatropic rearrangements. Problems involving sigmatropic rearrangement can be somewhat tricky and complex. If you are in a position to identify the carbon framework or the molecular framework that undergoes the sigmatropic rearrangement, it will be easy for you to identify the rearrangement process itself. So let us look at some examples of rearrangement reactions involving Cope and Claisen rearrangement. Here is an example. Write the product of Cope rearrangement of the following system. So this is the molecule that is given with the trans bond between these two cyclopentene hexamethylene cyclopentene rings. So first thing you need to do is to identify the 3,3 system, because it is already clearly mentioned that it is a Cope rearrangement. So the 3,3 system, essentially you start from the terminus 3, 2, 1, 1, 2, 3. So this is essentially a 3,3 sigmatropic rearrangement. In other words, if you look at this molecular fragment here, this is the hexa 1,5 diene is what we have. Hexa 1,5 dienes undergo the Cope rearrangement under thermal conditions by a suprafacial manner. So essentially the connecting the 3,3 bond and cleaving the carbon number bond 1,1 bond and rearranging the pi bond into the 1,2 position is what this reaction is all about, and the rearrangement is shown in this particular manner. The 3,3 sigmatropic rearrangement is shown by means of arrows, resulting in the formation of the methylene bridged cyclopentane derivative, which is this particular derivative. If you want to go one step further and show the cyclic transition state, you can do so. You can see here the hexamethylene derivatives are forming part of the chair form of the cyclohexene derivative. The chair form of 6-membered cyclic transition state involving the chair type of a conformation is what is very clearly shown. It also shows these two hydrogens to be anti or trans with respect to each other. So essentially, if you form a bond between this carbon and this carbon and break this carbon-carbon bond, then you get this product in a 3,3 sigma involving a 3,3 sigmatropic rearrangement kind of a reaction in this particular example. Now here is an example. You are asked to identify the product of this particular reaction. The reaction essentially involves this alcohol being treated with potassium hydride in THF and heated to about 50 degrees or so, and what is a kind of rearrangement that is going to take place. When you treat the alcohol with potassium hydride, you are going to get the potassium alkoxide as the product. The potassium alkoxide, of course, is part of a 3,3 anionic oxycope kind of a 3,3 sigmatropic rearrangement system. This is a sigma bond. If you look at this carbon 1, 2, 3, 1, 2, 3. So this is a 3,3 system involving a hexadiene kind of a system, except that this looks like these bonds are far away from each other. But remember, this vinyl group is endo in nature. As a result of that, the endo can approach this particular carbon quite readily through a cyclic transition state. So the 3,3 sigmatropic rearrangement is shown by means of arrows in this particular case, resulting in the formation of this particular structure. What is this structure? If you count the number of carbons in each of this ring, first of all, this is a 2,2,2 bicyclic, bridged bicyclic system. You are breaking the bridge here, so naturally it becomes a fused bicyclic system instead of a bridged bicyclic system. The fusion ring is starting from here, so that will be 1, 2, 3, 4, 5, 6. The other side also it is 1, 2, 3, 4, 5, 6. So it is a 6 and 6 fusion with the two hydrogen being cis with respect to each other. So this molecule is nothing but this particular perhydro derivative of the naphthalene. In other words, this is a decalene kind of a system. Tetradehydrodecalene, you can say, for example. The two hydrogens are cis because essentially this hydrogen and this hydrogen point in the same direction towards the back side of the skeleton, and the potassium alkoxide, which is an enolate, is generated by the 3,3 sigmatropic rearrangement. Upon workup, go to the keto form through the enol formation via the keto-enol tautomerism. It results in the formation of this particular ketone. So essentially a 3,3 anionic oxycope 3,3 sigmatropic rearrangement reaction is what this molecule is capable of undergoing, and that is illustrated by the mechanism as well as the stereochemistry of the rearrangement in this particular instance. Now this is another question. What if you take this allyl vinyl ether and heat it to 195 degrees Celsius? Because it is allyl vinyl ether, this is clearly a Claisen system. The Claisen rearrangement is what will take place under this condition. The Claisen rearrangement is represented by means of mechanistic arrows to show this transformation in this manner. That results in the formation of the transfer of this vinyl oxy group onto the alpha, beta, gamma, delta, gamma position of the allylic, the terminal position of the allylic ether. In other words, the vinyl oxy unit is transferred onto the terminal carbon of the allyl fragment of this vinyl allyl ether, resulting in the formation of an aldehyde, which is nothing but a gamma delta unsaturated aldehyde. Remember, the Claisen rearrangement gives a gamma delta unsaturated carbonyl derivative depending upon what kind of a Claisen rearrangement it is. The above problem can be also asked from the organic synthesis point of view. How will you transform this allyl alcohol to this particular aldehyde? What is easy to recognize in this particular instance is this is an allyl alcohol to start with, and this is a gamma delta unsaturated carbonyl compound. These are the two information that one need to gather in this transformation. So from the retrosynthetic point of view, if you look at how to do this transformation, you first convert the allyl alcohol into an allyl vinyl ether using mercuric sulfate as a catalyst and the vinyl transfer agent, namely the ethyl vinyl ether. So a trans-etherification reaction is carried out. Once the trans-etherification reaction is complete, you heat it strongly to high temperatures to about 195 degrees Celsius. The 3,3 sigmatropic rearrangement will essentially give you this product. So one can ask this question as a mechanistic question. One can also ask this question as a synthetic transformation question. Depending upon how the teacher views this particular question, the question can be framed accordingly as a synthesis problem or as a mechanistic problem. Now here is an interesting question. Optically active diene, which is shown here, this is a diene that we are talking about, undergoes racemization on heating to about 50 degrees Celsius. What is important to recognize here is that it is again a hexadiene system, and it is a hexa 1,5-diene system capable of undergoing a Cope rearrangement. So you write this in the chair type of a conformation. Essentially it's a transdecaline kind of a conformation is what is written here. So that is the diene system that is capable of undergoing a 3,3 sigmatropic Cope rearrangement. Once the Cope rearrangement takes place, the bond is formed between these two carbons. The carbon-carbon bond here is cleaved and the double bond is shifted to the adjacent carbon, resulting in the formation of this particular molecule. What is important to recognize is that this molecule and this molecules are mirror images of each other. So if an optically pure isomer of this molecule is taken and heated, it will undergo racemization, because once the reaction starts to go in the forward direction, the reverse reaction is also equally facile. Energetically, the reverse reaction has the same energy of activation as the forward reaction. So essentially one would establish an equilibrium between the starting material and the product that is formed. What is important to recognize is that the starting material and the products are having mirror image relationship. In other words, they are enantiomers of each other. So once you have 1:1 mixture of enantiomers, then that is essentially racemization process. That is why this molecule on heating gives the mirror image product, and hence the racemization takes place quite readily because of the reversibility of the Cope rearrangement in either direction to be favorable under this. This is a degenerate Cope rearrangement, except that the degeneracy is lost because of the fact that you get an optical antipode of the starting material, not the same configuration of the starting material. The mirror image relationship is very clearly seen in this diagram, where this dashed line is actually the mirror plane. So this is essentially reflected on the other side as a mirror relationship, and they are non-superimposable mirror relationship. That is why they are called enantiomers in this particular case. So 1:1 ratio of enantiomers is what is called a racemic mixture. So the process is known as racemization process. Some interesting structures are shown here. In the planar form, the structures are shown. They are hardly planar molecule. In a minute we will see that these molecules have a fairly complex geometry. The question is, the following molecules undergo degenerate rearrangement. Write the mechanism and show the degeneracy of the reaction. In other words, you start with this molecule, do a rearrangement, end up with the same molecule is what you need to show. Now this molecule here is essentially a cyclopropane connected to two vinyl group, and the third carbon of the cyclopropane is connected to a carbon. So a cyclopropane with the two vinyl group, the third carbon is connected to the another carbon which is connected to the ends of the vinyl group, for example. So this is the actual molecule in terms of the conformation of the molecule or the shape of the molecule. This molecule this is like a divinyl cyclopropane derivative, so it can undergo 3,3 sigmatropic rearrangement with the formation of a carbon-carbon bond between these two carbon. The 3,3 system is shown clearly in the red ink color. So the 3,3 sigmatropic rearrangement is what is taking place, and the starting material and products are essentially same. That is why it is a degenerate molecule. So that is the purpose of this reaction, to be shown to be a degenerate molecule in this particular case. The second molecule is this particular molecule. This molecule has this particular geometry and shape. It is better to number this molecule starting from here 1, 2, 3, 4, 5, go around the ring up to 8. 9 and 10 are the bridging atoms of this particular derivative. So what is that 3,3 sigmatropic component? It is very clearly shown in the red. This is 1, 2, 3. Here also you can write this as 1, 2, 3. So this 3, 3 is going to be the connectivity between carbon number 3 and 6. If you connect carbon 3 and 6 and break carbon 1 and 8, you will get the 3, 3 sigmatropic product. So that is the structure that is shown here. This structure is essentially same as the starting material structure, which is this structure, except the numbering has to be followed correctly. The carbon 3 and 6 are connected, so you can see carbon 3 and 6 are connected. Carbon 4 and 5 will essentially form the bridge, which is this methylene bridge here. So 4 and 5 forms the methylene bridge. Carbon number 9 and 10 are already connected, so they will remain connected. The double bond is shifted between 1 and 2 and 8 and 7. So you can see between 1 and 2 and 8 and 7, the double bonds are shifted. So essentially this is redrawn in the same way as it is redrawn originally. Hence it is a degenerate rearrangement. This molecule is same as the starting molecule in spite of the fact it has undergone 3,3 sigmatropic rearrangement. Such rearrangements can be studied by NMR spectroscopy or by suitable deuterium or carbon-13 labeling to show that this carbon-13 label scrambles during the course of the 3,3 sigmatropic rearrangement. Here is another interesting example. This molecule essentially is 1,4-hexamethylene cyclohexane molecule. This should exist in the boat type of a conformation in order to bring this carbon number 1 and this carbon number 6 in close proximity to undergo a 3,3 sigmatropic rearrangement. You start numbering from here 3, 2, 1, 1, 2, 3, or you can say 3, 2, 1, 1, 2, 3. So this is actually the hexa 1,5-diene system. Either the top portion is a hexa 1,5-diene system or the bottom portion is the hexa 1,5-diene system connecting either these two carbons or these two carbons. So if you write it in the boat conformation, you can bring carbon number 1 and 6 in close proximity. Hence the reaction can take place through this particular transition state, resulting in the formation of this particular product. The product is shown as to be the same as the starting material. In other words, if you start numbering it, again the numbering will correspond to this particular structure being equivalent to this particular structure. Now what cannot undergo a rearrangement through a cyclic transition state is the chair form of the hexamethylene 1,4-hexamethylene cyclohexane. So the conformation has to be, although this may be a favorable conformation, there will be certain population of the boat type of a conformation in this molecule, which will trigger the reaction to go in this direction to a sigmatropic rearrangement, which is of course a degenerate rearrangement. Overall you don't see any reaction, except if you do a deuterium labeling at this position, you can see the scrambling of the deuterium labeling in the product to all the other positions also. Here is an interesting example to illustrate the retention of stereochemistry during the course of a 3,3 sigmatropic this is not a 3,3 sigmatropic rearrangement, I am sorry, it is a 1,5 sigmatropic rearrangement. This is a 1,5 sigmatropic rearrangement because of the fact this is a substituted cyclopentadiene molecule. So this bond is cleaved, so this is 1 and 1, 1, 2, 3, 4, 5. So this is a rearrangement which involves not 3,3, I am sorry, please correct this. This is a 1,5 sigmatropic rearrangement, resulting in the formation of the product, which is this particular product. The mechanism of the rearrangement is very clearly shown here. So this is a carbon-carbon bond that is breaking, and it is a suprafacial migration. So suprafacial migration should take place with the retention of stereochemistry at this particular carbon. So the stereochemistry is retained, which is inferred by the fact that initially you start with the cis dimethyl derivative, you also end up with the cis dimethyl derivative, which indicates the stereochemistry here is retained during the course of the migration. So it is a suprafacial component with respect to the pi system, as well as a suprafacial component with respect to the sigma system, involving a 1,3, 1,5 kind of a rearrangement involving 6 electron rearrangement to give this particular product. Remember, here there is a hydrogen. This is also a monosubstituted cyclopentadiene. These hydrogens can now migrate to 1,5 shifts. So this can in fact further undergo many 1,5 sigmatropic rearrangement reactions during the course of the heating of this molecule. Now here is an example of again a anionic oxycope rearrangement. This is a divinyl cyclobutane derivative. The divinyl cyclobutane derivative on treatment with potassium hydride gives this potassium salt of this alkoxide. This can readily undergo 3,3 sigmatropic rearrangement to give this product, which on workup essentially gives this macrocyclic ketone. Please remember that this is not a violation of Brett's rule. This is actually a bridgehead double bond, because this is a larger ring system. This is involving 1, 2, 3, 4, 5, 6, 7, 8 membered ring system. So it is a this is actually 1, 2, 3, 4, 5. 5, 3, 1 bicyclic ketone is what is formed in this particular case. Because of the large ring size, this double bond can be accommodated at the bridgehead. So it is not a violation of Brett's rule, because Brett's rule is applicable only to smaller bridged ring systems, bicyclic ring systems of the type 221 and 222 type of bicyclic ring system. So this is essentially an anionic oxycope rearrangement involving the formation of the alkoxide in the 3 position, resulting in the rearrangement taking place at around 50 to 60 degrees or so. And upon workup, this enol essentially will go to the ketone, resulting in the formation of this final product. Now here is an interesting reaction. These two molecules are heated together in the presence of an acid, and it produces citral. Citral is a industrially very useful compound. This is used in fragrance industry. It is also used as a starting point for the synthesis of vitamin A. In fact, BASF produces or manufactures the citral using these two compounds as starting material. What is the mechanism that is involved in the formation of citral from this starting material is what? If you add up the molecular formula of this molecule and molecular formula of this molecule and subtract it from the molecular formula of this molecule, you get one water molecule. So essentially this is undergoing some kind of a condensation reaction followed by dehydration reaction followed by certain molecular rearrangements to give this particular product. What are the possible reactions that can take place? When this aldehyde is treated with this alcohol, it can form a hemiacetal. The hemiacetal can undergo alpha dehydration from the alpha position in this particular way, resulting in the formation of the allyl vinyl ether. So this is a pyrenyl vinyl ether is what is being formed in this particular instance. This is a 3,3 sigmatropic Claisen kind of a system, so it can undergo the 3,3 sigmatropic rearrangement to give this particular product. Once this product is formed, if you rotate this carbon-carbon bond, essentially you get a cope system. So you get a hexadiene system, 1,5-diene system, which is a cope system. So this is only a conformational change between these two structures. So once this structure is formed, this undergoes the 3,3 sigmatropic rearrangement to form this molecule. This is essentially citral. You can see here gem dimethyl vinyl group with a CH2 and then a methyl group, double bond and CHO. Gem dimethyl group with a vinyl, CH2 with a methyl group here, and a vinyl and a double bond aldehyde is what is formed. So this is essentially manufacturing process of citral starting from these two C5 molecules that are shown in this as starting material in this particular case. So I hope you enjoyed this problem solving session. We considered several 3,3 sigmatropic and 1,5 sigmatropic rearrangement. The essential point that I would like to inform here is that when the Claisen system or cope system is given, it is better to identify the hexa 1,5-diene system or the allyl vinyl ether system and number it properly and proceed with the 3,3 sigmatropic rearrangement. The case of 1,5 sigmatropic rearrangement, make sure that the reaction proceeds with the retention of stereochemistry for carbon migration. One example was shown in this particular tutorial, and that's all I would like to say in this particular module. Thank you very much for your attention.